Hello and welcome to this video on forces. Specifically, we're talking about ramps again. One of the struggles with ramps, or one of the things we need to talk about, is how the acceleration works and how the forces interact. For each picture here, we're going to talk about two scenarios. The first being with the block moving down the ramp, or in other words, V going this way. And in the second, we're going to have V going this way. Now for this setup, without any friction being a factor on a smooth ramp, the acceleration is the same either way. There's only one force acting in the x direction, and that's this little chunk of the force gravity here, pointing down. In this case, no matter which way the velocity is going, the acceleration, or the net force, is going this way, which would speed this box up or slow this box down. This is only if there's no friction or no applied forces. But what happens when there's friction? Well, once there's friction, which way the box is heading matters. The first scenario, V downward, is for when the box is standing still, or for when the box is moving down the ramp. Both are equally relevant here because in this case, that's the way the box will start heading if there wasn't for friction. Both cases in here, with V going down the ramp, friction goes this way. What about when the box is sliding up the ramp? Say it started down here and started sliding up the ramp and encountered it. Which way is friction pointing? Well, in this case, friction is always opposite the direction of travel. So, therefore, friction will be going down the ramp. For this situation over here, which way the acceleration is pointing depends on the force friction. The force friction might be larger than the force gravity in the x direction, which would cause it to slow down as it slides down the ramp, or the force gravity in the x direction might be larger than the force friction, causing it to speed up as it goes down the ramp. Or they might be equal, causing the acceleration to be zero, either constantly moving at a constant velocity down the ramp, or not moving down the ramp at all, depending on what the initial velocity was. Either way, the acceleration, we don't know. This is the scenario we dealt with primarily in the first video. But the second scenario is what we're primarily going to focus on today. In this scenario, the velocity is heading up the ramp, which means that in the x direction, both the frictional force and the force of gravity are pointing down the ramp. In this case, no matter what the values are, the acceleration is going to be going down. This block is going to slow down as it slides up the ramp until eventually it's going to stop. At which point we need to ask, does it stop and stay still? Or does it stop and then turn around and start falling down the ramp? This scenario is the one we're going to focus on today. So let's take a look at a sample problem about this. Okay, so here we have our example problem. 10 kilogram block slides up a steel ramp with a 30-degree slope. Its initial velocity is 6.84 meters per second. A, how far up the slope does it go? B, once it reaches that height, does it stay there or come back down the ramp? And C, if it comes back down the ramp, what's its acceleration? Let's take each of these in turn. We'll start with A. How far up the ramp does it go? In other words, what distance or displacement does it travel? This is a kinematics problem at its core. What is delta x? We know our initial velocity. It's this 6.84 meters per second. We even know the final velocity. How far up? Highest point is going to be 0. At the highest point, your v final is going to be 0. So v initial is 6.84. The v is going to be 0. And I'm looking for my delta x, or my delta in the direction of the ramp. The only problem is I don't have t or a. But I can find a using my forces, using my equations from that. So what I want to do here is I want to start with my free body diagram. So instead of having this just here, I'm just going to put it on the ramp and draw my free body diagram for it so I can find my acceleration. In this case, put my coordinate grid on. What are my forces? Well, it's going up the ramp. My v is this way, which tells me that my frictional force is down the ramp. And then my normal force is also going to be perpendicular ramp along my coordinate system. So force normal, force friction, force friction. The only force left is gravity, which points straight down always here. And in case you forgot, what we're going to do is we're going to rotate this entire thing so we can go find our forces here. So in the y direction, I have this force normal and part of force gravity. This part, to be specific. In the x direction, I have force friction and force gravity.
Or at least it's part in the x direction.
Okay. So let's rotate this back and write down those equations. Sum of all forces in the x direction is my mass times acceleration in the x direction. And we said that was force gravity and force friction. Now we have to pick a direction here. Whatever direction you pick to be positive, be that down the ramp or up the ramp, stick with for the entire problem. My recommendation is whatever direction the velocity, the initial velocity is pointing in, call it positive. So if initial velocity, which is up the ramp, is positive, down the ramp, which means my force friction, and my force gravity in the x direction are both negative. If you do this problem and say that your forces are positive, your velocity is negative, you'll get the same answer, just be careful. In the y direction, surprising no one, my sum of all forces in the y direction is MAY, which is going to be my force normal minus my force gravity in the y direction. We've been through this a few times, but let's go ahead and do it. This is my FGY, this is my FGX. This is my angle, which is 30. So if I take this triangle and blow it up over here, FGX is on the opposite side, FGY is on the adjacent side, so FGX over FG equals sine theta in this case. FGY over FG equals cosine theta in this moment. Additionally, my block is moving along the ramp this way, it's not moving up and down, or more accurately, my acceleration in the y direction is 0. So let's go ahead and plug that in. I'm also coming over here and substituting in my normal force times mu for my force friction. And there we have it. So now all I need to do is solve for my acceleration. I can find my normal force, I can find my FG, I can find my acceleration. Go ahead, do that on your own, check back in. So if you go through this problem and solve it, the first thing you do is get your normal force equals mg cosine theta. You'll notice I plugged in mg for force gravity. Once I had that, I came over here and plugged that in for my normal force here. Again, making that substitution, mg is equal to my force gravity. Giving me m times the acceleration in the x direction equals negative mu times mg cosine theta minus mg sine theta. M is in every term, so I just divided it out, got rid of it. I didn't actually need the mass for this particular part of the problem. Maybe I'll need it later. Leaving me with my acceleration in the x direction equals negative mu g cosine theta minus g sine theta. At this point, I just went through and plugged in my numbers. Mu is negative 0.57 because my mu kinetic, since it's sliding, is 0.57. I want to use this one for right now. We'll talk about why we use the 0.74 or when we use the 0.74 in a bit. Times 9.8, which is g times cosine theta minus 9.8 sine theta. And there you go. Plug that all in, you get negative 9.74 meters per second squared. Now this isn't your answer. This just lets you get your answer of finding delta x. But that's a kinematics problem. That's fairly easy at this point. In fact, go ahead, do so now. I get 2.40 meters, works over here in blue. Had you done this with the velocity being negative and your acceleration, which would give you a positive acceleration because this would be positive F, positive G, you get a negative displacement, which means you're heading up the ramp. Either way, same number, just same answer, just different logistics. So that's how you solve the first one. It's the same problem we've been doing combined with the problem from a previous unit. In this case, you can talk about how the acceleration is found from the forces and then plug it into a kinematics problem. It's still set up your free body diagram, label your forces, set up your sum of all forces x, set up your sum of all forces y, and solve through. There's just a little extra. So that's A. Let's talk about B. First, let's get all this stuff out of here. So now that we have this on the ramp, as it slides up the ramp, it's going to slow down, slow down, slow down, and then stop, and then but for an instant before it would start turning around. At least that's how airborne objects work. You throw it up, it's going slower, 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 it'll stop, and then turn around and come back down. But in this case, because it's touching a surface, it'll stop for about a moment, and that frictional value will change. Because it's not moving anymore, it'll change from that static value to that kinetic value. So now, at this instant where it's at the top, we're on B, we want to look at if it starts moving again using mu static, which again, for steel on steel, is 0.74. And here, we draw our free body diagram, we set it up. The only difference this time, besides my inability to draw, is that which way is friction pointing? Because the normal force is still going to be up perpendicular to the surface, and gravity is still going to be straight down. But in this case, friction acts to oppose motion. Which way is the unbalanced force? Well, the y forces are balanced out up and down by normal and force gravity y, but Fgx is unopposed, which means that my frictional force has to be heading up. The friction flips, and suddenly we're doing the problems we did previously. In fact, B and C are the exact same problem we had done in the previous video, only this time there's a little lead-in. Go ahead, go through this one. You've done it before, you can do it. Solve this one out. Okay, if you go through and do the math, as outlined on the screen, you'll find that the frictional force, the maximum value for the frictional force, is 13.80 newtons larger than the force provided by gravity in the x direction, which tells you that the block doesn't start moving again, solving B and making C invalid. This only works if you use the mu static. Had you used the mu kinetic, you would have said, it starts moving, then you would have gone on to do C. But because it stops for that moment, you have to use the 0.74. As a kind of follow-up note, had you done the extra practice challenge and figured out the tangent shortcut for angles, you could have done that and it would have told you right off the bat that the 36.50 is the angle needed to make this block slide on the steel on steel surface. It's at 30 degrees and wouldn't have moved. That's the shortcut answer. And there you have it. That's how these slightly more complicated problems work. Just have one more thing to show you really quick. Let's talk about friction and applied forces. So again, we're talking about if the velocity is down the ramp or up the ramp. The question is, how does the acceleration factor? In both cases, we've already talked about how the friction works. The friction is up in this case, and the friction would be down in this case. But the one thing we haven't factored is what if there's, say, a rope pulling it up the ramp? Or what if there is a bungee cord slowing it down? In both these cases, we have to add a force. We have to add a force applied. And depending on which way the truck is moving or the box is moving, if it's moving down the ramp, like so, or up the ramp like so, and which direction the force is pulling determines how we set up our equations. So, for instance, in this case, if let's say we had a force pointed down the ramp, my sum of all forces in the x direction would be the force applied plus the force gravity in the x direction minus the force friction. Whereas if we had it pulling down the ramp in this one, my sum of all forces in the x direction would all be negative, minus force friction, minus the force applied, minus force gravity in the x direction. Back that up for a second. If the force applied was pulling it, say, up the ramp or slowing the descent over here, or pulling it up the ramp in the direction of the velocity here, the process is still the same. The only difference is my sum of all forces in the x direction here, be FGX minus FA minus force friction. And over here, it'd be sum of all forces x would be the force applied minus the force friction minus the mgx.
That should say force gravity in the x direction, not mgx, to be very specific and accurate. Apologies.
Adding an additional force only changes how you set up the equation very slightly. And if the force is added, we can, or if we want to solve for it, we can do it that way. Some of your practice problems will look like this. Anyways, thanks for watching. Have a good day.